Hi, I'm Shahnamaz. In this lecture, we are going to study the bilinear maps. But before going to introduce the notion of these maps, let us prove the following result. So, let us consider an R module, say P. So, an R module P is projective if and only if every exact sequence zero goes into A to B, B to P, and P to 0. This is map phi, this is psi. So if and only if every exact sequence splits. Here A and B are R modules. Let us recall what do we mean by an exact sequence to split. So if we have exact sequence like this, so if A and B, A, B, C are R modules, so this is an exact sequence. Suppose this is map phi, this is map psi. So we say that this sequence, this exact sequence is actually a separate exact sequence if there exists a map, say T from C to B, such that psi composed with T is identity on C. In that case, this sequence is said to be a separate exact sequence, and there is a consequence that if this sequence is separate exact sequence, then this B is actually direct sum of A plus C, A and C. So this is what we have to prove. So let us prove this. So first we will assume that P is projective, and we prove that this sequence separates. So assume that P is a projective R module. So if this is the case, then if we look at this map here, psi, which is surjective, then for the surjection, psi, which is a map from B to P, the induced linear map psi substar, which is map from home PB to home PP. So this is surjective. This is characterization of projective modules. So this is surjective. Now one can look at this set here. So if this psi star is surjective, that means for every element here we have a pre-image here. So one can note here that we have the identity homomorphism from P to P. So for that identity homomorphism we have a pre-image here. So therefore for the identity homomorphism on P, which is an element here, there exists an element here. I mean, this element has a plane image here, so there exists some element, say F in PB, such that this psi star F, this is identity on P, but this psi star F is psi F. So this F is an element from P to B. So that means, now consider this sequence here. Now consider the sequence, the exact sequence 0 goes into A goes into B, and B goes into P goes into 0. Here we have the map phi, and this is psi. So this is our sequence. Since we have a map like this from P to B, which is from P to B, which is F here, because F is an element here. I mean, that means F is a linear map from P to B. Since phi composite with psi is identity map, so since this F composite with psi is identity on P, we note that this sequence is separate exact sequence. So this is the separate exact sequence. Now let us assume that P is projective, and so this proves that this sequence is a separate exact sequence. Now let us do the converse. So conversely, let the sequence, let every sequence, conversely let every exact sequence of the form 0 goes into A goes into B goes into P, and P goes into 0 splits for any R modulus in B. And what we have to prove? We have to prove this P is projective. Now let us, since every R module can be expressed as a quotient of a free module, so we can express this P as a quotient of a free module. So express P as the quotient of a free module with kernel K. That means this P is actually isomorphic to, so let us express P as a quotient of a free module, say F with kernel K. Then if this is the case, this P is isomorphic to F mod K. So if this is the case, then we have this exact sequence, then the sequence zero goes into K, where K is kernel, K goes into F, and F goes into P, P goes into 0. Obviously this is the exact sequence. Here this is the inclusion map and this is the canonical map pi. So this is the exact sequence, but at the first place we have assumed that every sequence of this type splits. So here we have P and there is no restriction on A and B. A and B can be arbitrary modules, so in place of A and B we have K and F. So by assumption this sequence splits. So the sequence is obviously exact. Hence by assumption this splits. Hence by assumption let us denote this by star. So the sequence and star splits. I mean the sequence star splits. Now if this sequence splits, that means this F, this is actually direct sum of P and K. Now F being free module and P being a direct summand of a free module implies that P is projective by definition of projective module. Hence P is a projective module. Therefore if every sequence like this splits, then P is always a projective module, where A and B are arbitrary or modules. Now let us define the bilinear maps. What do we mean by bilinear map? So let us consider R modules A and B. So let A and B be R modules. So a map f from the Cartesian product of A and B to any R module M. So this M is an R module. So this bilinear map, and this map is said to be a bilinear map if for each x1 x2 in A and y1 and y2 in B, we have the following. I.e. f of x1 plus x2 y is actually f of x1 y plus f of x2 y. So this is true for some y in B. Similarly, f of x y1 plus y2 is f of xy1 plus f of xy2. Here x is in A. So this is first condition, this is second. Now third condition is like this. So if we choose an element, say A in R, so f of A x y should be equal to A of fxy, where this A is an element of R and x is an element of A, y is an element of B. And finally f of x a y, this is A of fxy. This is again true for all A in R, x in A and y in B. So basically a bilinear map is a map which is linear in both components. I mean which is R linear in both components, and first component as well as in second component. So one can rewrite this definition like this. So this is same as to say, so this is so let us make this remark. So this is same as to say f, which is a map from A cross B to M, is a bilinear map if for each fixed x in A, the function which takes y to f of xy is R linear. And for each fixed y in B, the function which takes x to f of xy is also are linear. So here this is for some fixed y, again this is for some fixed x in a, for some fixed x in a. So this is called a bilinear map.